Hi, I'm Diogo Medeiros, and today I'm going to be talking about the retrieval of atmospheric columns of greenhouse gases in the metropolitan area of São Paulo using Fourier transformed infrared spectroscopy. So let's have a look at the principles of the technique. The sunlight reaches our atmosphere and it crosses through it, and when it does that, the many components of the atmosphere are going to interact with it. They're going to absorb very specific wavelengths of the light. So if we assume that on the top of this building in the middle of the figure there is a spectrometer, this instrument is going to collect the sunlight and record a spectrum of the light, which contains information about the many components that absorb the light on its path. Our job from here is try to extract this information from the spectrum, working backwards to generate information on the many components that were on the path of the light. The procedures which are used to deal with this task are referred to as atmospheric inversion algorithms. Let's have a look at how these algorithms work. So the figure on the right represents an experimental measurement, and the whole procedure starts with an educated guess for the vertical profiles of the many components. The figure on the left shows an example of a profile for CO2. It's just an educated guess which is generated from many things, including profiles that were tracked using balloon flights, meteorological parameters, and surface measurements. The guess can then be translated into a spectrum using the Beer-Lambert law. So the red line on the right represents the projected spectrum that is expected if the column that we guessed is the real existing column. But as we can see, there is a certain gap. There's not a good match between the blue, the experimental measurement, and the projected spectrum that would be expected for our guessed column. Which means our guess is not very good, we have to adjust it. And because we are underestimating the spectrum, we're going to increase the concentration. We're going to scale up the column. When we do that, we've done it too much in this case. We've got the green line, and I think you've got the idea. Somewhere in between the two guesses that we had, there's going to be a much better guess that is going to represent well the experimental measurement. And that's what the black line represents in this case. The resulting profile on the left, in black, is our best estimate for the column of CO2 using an inversion algorithm. The search is usually done using a nonlinear regression algorithm. If we have the column like we have in the left here in the figure, we can do lots of things with it. We can integrate it to get, for example, the total concentration of CO2, but we can also generate things like the dry air mole fraction of CO2, which is something that is measured by satellites, so we have ways to compare our measurements with satellite data and provide ways to validate the satellite measurements. So let's have a quick look at some preliminary results that we've got. These are the dry air mole fractions for CO2 in two different days of 2020. We have data for methane and we have data for CO. In terms of future work, we have to set up an automated weather protection. The instrument is very fragile, it can't get rain on it, so we have to set it up. With that setup, we'll be able to collect and analyze data on a daily basis, which will be great. We want to test multiple inversion algorithms, and finally, we want to estimate the contribution of the metropolitan area of São Paulo to the global carbon emission budget. And I would like to acknowledge my supervisor, Professor Márcia Kemi-Amassoi, the principal investigator of the project Metroclima, Professor Maria de Fátima Andrade, and the collaborator to the project, Professor Eduardo Landulfo. And thank you very much.